I'd like to introduce our next application model. This is the industrial CFB combustor. But first, I'd like to acknowledge my colleague Keshav Ramchandran. He's the lead modeler on this work, and I'll be presenting it today. All right. So I'm going to be dividing this talk into three different sections, starting with an introduction to the technology of circulating fluidized bed combustors, or CFBCs. I'll then talk about sort of the purpose of this application model, why Barracuda Virtual Reactor is uniquely positioned to model it, and sort of what is the CFD value proposition for modeling a CFBC with Barracuda. Then I'm going to dive into three different cases ranging from a 50 kilowatt lab scale system up to a 110 megawatt industrial scale system, showing sort of this, the range of different industrial sizes that can be used with Barracuda, as well as an extension of this work to an additional case with ammonia co-firing. And that really is sort of the heart of these application models, is that you'd be able to take them, download them, and make your modifications in order to optimize your system, which in this case are those emissions reductions. All right, so let's talk about CFBCs. CFBCs are furnaces that are intended for efficient, low-emission combustion of solid fuels. And so primarily that consists of coal, but this also extends to a range of solid fuel types like biomass. How this works is there's a high-velocity airstream that's fed in through two different locations, one through this primary air inlet, and then another through this secondary air inlet. That produces a combustion when in contact with the fuel fed in here. And then that interacts with a bed consisting of ash and limestone. And then this sort of circulating fluidized mixture of solids circulates through the bed. It goes up the furnace. It travels through the cyclone, and it returns back to the bed through that cyclone. So with this circulating system, you have high gas residence times. That really helps to make this process very efficient. We get good temperature uniformity. In addition, with this exothermic combustion reaction, we can recover a lot of that heat and apply it to different processes as well. All right, so I want to point out there are basically two dominant technologies for solid fuel combustion right now. This is the CFBCs as well as the pulverized coal combustion. And one of the advantages that I alluded to is that CFBCs can operate with a wider variety of solid fuel feedstocks. That includes these low-grade coals, biomass, industrial waste. With pulverized coal combustion, you're sort of limited to a more narrow window of solid fuel types that you could use. CFBC, once again, with that high residence time, we get efficient mixing, good incomplete combustion for this process. We also see that with CFBCs, these operate on average much lower temperature than traditional pulverized coal combustion. These operate around 850 to 900 C, compared to pulverized coal, which is around 1300 Celsius. And that really helps with our emissions problem. We can minimize the formation of these NOx species, and the usage of these sorbent materials, which is limestone in this case, can be used to capture undesired SO2 emissions. All right, so I want to talk a little bit about sort of main applications of this technology. We see it primarily used in power generation, but this is also in recent years, we see this applied to industrial process as well as waste to energy. And so you can imagine operating a circulating system like this. There's a lot of operational challenges that you'd want to consider. You have some very complex physics with these fluid particle flow coming into this furnace, very complex network of chemical reactions you might imagine. You also have a range of pollutants that are released from this process, and so we want to take care to ensure that our operating conditions and our design is optimized to minimize those pollutants. You may experience, with poor design, you might see inefficiency as a result of mixing or temperature non-uniformity, so you want to take care to ensure that the circulation is consistent in this system and we have good mixing behavior. In addition, anytime you have this high velocity solids entering in through this furnace, you do have a risk of erosion potential. And so we want to take care to make sure that we minimize that potential. So really the value proposition of Barracuda or CFD is that we can actually look into the system, understand the dynamics, and we can actually start to troubleshoot potential operational problems, make design changes, and then ensure that if we do make these changes, we can do it with minimal risk and with high efficiency. All right, so this, many of you are Barracuda users already, so this is probably a review, but Barracuda allows us to get a full picture of the three-dimensional internal dynamics inside of this combustor system. We have reaction kinetics that we can implement in all the way across the system, specifically relating to these undesired pollutant emissions. This is a sort of something that we want to be conscious of in our modeling, that we can minimize the amount of those pollutants. And ultimately, the goal here is that that understanding will lead to us being able to solve potential operational problems that might happen, like that combustion inefficiency or temperature hotspots and erosion. And so after those problems are identified, we can actually look towards improving the design. And Barracuda is a useful tool for looking at a design space, being able to test over it with minimal risk and minimal cost. All right, so I mentioned I'll be talking about 3 different cases, starting with this lab scale system. This was based on a paper by Wu, 2017. Very small. This is a 4.2 meter tall riser. It's a small diagram of it is shown here. So we used this model as a sort of a lever to validate our reaction kinetics. And once we had some confidence that those kinetics were correct, we moved on to this industrial scale system, this 110 megawatt, 28 meter tall riser. Both of these are separate application models on our website and can be downloaded and used. And then we moved towards this emissions reduction case, where we actually replaced 20% of that feed by mass in an effort to bring down our CO2 emissions by bringing in a less carbonaceous material. All right, I mentioned that the reaction kinetics are quite complicated for this process. I'll do a quick run through here. We have, the solid fuel comes in with a range of volatile materials. Barracuda allows us to represent the devolatilization in our software through that devolatilization model. And so, as the solid fuel interacts with the bed, it releases those volatiles. They can react in these pathways described on the rest of this slide. Specifically, we want to be aware of that NOx formation, because those volatile materials can react with oxygen to produce those undesired NOx emissions. We have combustion of some of those, one of those volatile species, which is that methane. And so, this sort of describes the full suite of what we could expect in this combustor. We have the gasification and combustion of our char material, as well as some associated reactions that we can expect here. I do want to highlight our sulfur capture as well. So we do model in this CFBC process the capture of that undesired SO2 emission. All right, so I mentioned that we started off with this 50 kilowatt case. This is a very simplified study. It's sort of a tube here where we have a feed of this primary air inlet that interacts once again with a bed of that ash and limestone material. Cold feed comes in here, secondary inlet right above that. And we see here that we're able to sort of get an idea of how the kinetics are being modeled in the system, make sure we can match the data being produced by this lab scale experiment. I did want to mention we do use a thermal wall BC here. This is, we want to make sure we can capture the heat transfer from this process, and so we're able to use sort of a newer model feature, which is that heat transfer resistance. So combustion happens here. The solid fluid particle mixture travels up the bed. it exits through this pressure BC, and then it's returned back to the bed here. And what we see on these two plots is that you have a pretty close agreement between the fluid temperature profile observed in our simulations and in the experiment. We also took a look at the flue gas composition, and so both the O2 and CO2 mixtures were matched quite well with experimental data. And so this gave us some confidence that we could then take this model and bring it up to a much larger industrial system. All right, and that brings us to this 110 megawatt example. This was sourced from Yang 2023 paper. This, once again, is that 28 meter tall riser, width ranging from that 2.4 to 5.4 meters. We use a compressible flow simulation with both discrete and volumetric chemical reactions. Similar to that pilot or lab scale example, we have primary air that comes in through FlowBC here at the bottom that interacts with the cold feed that comes in through these flow boundary conditions here. And that's primarily where the combustion takes place. Our secondary air inlets are located here. And then we have a pressure outlet here on the top where some of that solid material can leave as fly ash. And we also have a thermal wall BC here on the furnace itself. So we're bringing in coal at a rate of about 2.25 kilograms per second, and that bed consists of a mixture of that ash and limestone material. And the thermal wall BC is kept at a constant surface temperature of that 298 Kelvin, again with a heat transfer resistance defined there. All right, so I want to point out a few things here. Sort of the driving mechanism of this is that we want to have good circulation, because that means good uniform heat transfer. So this bed consists primarily of that ash and limestone. It's about 95% by mass. So you can see we have some pretty substantial solid circulation that we're seeing here. I do want to point out that this plot here shows the mass fraction of our volatile species. And so we can see this is where the coal feed comes in, consists of a mass fraction of about 0.24. Those volatiles are released very rapidly, and so those red particles dissipate quite quickly as they enter the bed. Also, the solid carbon reacts through those char reactions, and we see that sort of the presence of those red particles that have a higher mass fraction also begin to decrease, and we're left with blue particles that are much lighter, and they're more easily able to sort of transport up to the top of this bed and back through those cyclones. All right, and so one thing that I mentioned earlier was that the volatiles released from this process can react with oxygen to produce undesired emissions, specifically those NOx emissions. And so we want to try to minimize the amount of contact that those volatile species have with oxygen. And so we can see that the volatile species are primarily confined to around that secondary air inlet. And so I'll show, in the next slide, I'll show sort of the oxygen distribution as well, but there is not much time for the volatiles to contact that oxygen, and so that results in, more ideal NOx emissions. Oh, let's go back. All right, here I wanted to point out the oxygen mole fraction, and so we can see that is high here in the air inlet. This is the secondary air inlet and the primary air inlet. So that's reacted and consumed quite quickly. That's good. We don't want to see a lot of interaction of that oxygen with the volatiles. We have CO2 being generated also from the combustion. We see that the NOx does have a sort of a spike as it interacts with the oxygen, and then it stabilizes here to a fairly low level. And we have water that's being produced both from the reaction of the volatiles with oxygen as well as the combustion. All right, so then getting to this additional case, we wanted to showcase an example of how one might use an application model. And so you could take that base 110 megawatt example and start to adjust your feed conditions. In this case, we came up with a case where we replaced 20% of that coal feed with that ammonia. And the idea being to keep the same thermal mass as conventional operations. So this should be generating the same heat as we would see in a typical industrial, or as in that baseline industrial CFB. The air flow rate was slightly modified, but what we saw was that replacing a lot of that carbonaceous feed with the ammonia material, we could get a pretty significant reduction in our CO2 emissions. It's about 33% reduction compared to that baseline model. We do see an increase in the amount of steam being produced due to the fact that we have that additional hydrogen coming in through the ammonia. But you could imagine sort of testing over a design space, looking at different feed fractions of that ammonia and seeing how that might affect your product emissions. I did want to point out that this material is all available on the website. You can download it, you can start to make your own modifications and apply it to your system. So thanks, and open to any questions.
Thank you, Tanner.